Welcome to Flex Guard tutorial. Today we'll be doing a tutorial on structural design in steel. Structural design in steel. Steel is a very vital material needed in construction for vital reasons due to the properties it possesses, such as great strength, good ductility, high stiffness. It is very easy to fabricate, and among all, it is economical, it is relatively cheap. So today we'll be doing a mini tutorial on the design of steel beam, of which we'll be considering the 10 process involved in the design of steel beam using the Universal Beam British Standard 5950. So we'll use this tutorial to explain the necessary step needed for the calculation, needed for the design, the use of table and everything in this introduction video. The next video of which we're going to do some examples regarding the calculation, applying the necessary steps for design of beam. So the first step for the design of beams of steel beam include the determination of design shear forces FV and bending moment at critical points on the element. This method is very easy. It involves the use of strength material, the elementary knowledge in strength of material, finding your reaction, drawing your shear force diagram, bending moment diagram. From the diagram you can determine the design shear forces and the bending moment, the maximum bending moment. The second step is the initial section selection. For you to select any specific standard section for design of steel, you have to follow some formula, and the law states that our maximum bending moment should be less than the maximum capacity moment. Our maximum capacity moment can be gotten using the formula. We say that the moment capacity is equal to the assumed design strength multiplied by the plastic modulus of the section. But before that, you have to do a simple calculation to determine the section to pick, to determine your plastic section modulus using the formula. We say that plastic modulus X is equal to maximum moment capacity gotten from step 1 divided by the assumed design strength. From this, after getting your plastic modulus, you now go to the table to pick a particular section of your choice that is suitable or closest to the value you get, or exactly the same. And this can be used to select suitable universal beam section from the steel table with the plastic modulus section S greater than the calculated value. So this is the example of the table. This is the British Standard 5950 table for selection of a section. As you can see the plastic modulus axis, the elastic modulus axis, second moment of area, etc. on the table. After your calculation, you move to the row of the plastic modulus and pick a particular row to pick your section. You can see 915 by 305289. This is an example of the section to pick. You pick the suitable section of your choice. This is the second part of the table, and this table is specifically meant for universal beam selection. We have another for column selection, which is used to universal column. We'll deal with that subsequently when we are going to design for column. So the next step needed for the design is the the classification of section. And the classification of section is divided into two, which is the strength classification and the section classification. The same way we did for step 2 above is the same thing we are doing here, in the sense that we are using table. From your question, from your material, from your properties of the steel you are using, you will get the grade. From the grade you get your thickness. From there you can pick your design strength to know the design strength you are going to use for your calculation. From there, the second part, which includes section classification. The section classification is divided into 4. We have the plastic section, which is the class 1, the class 2, which is compact, class 3 semi-compact, and class 4 slender section. But mostly we come across plastic section and compact section in some cases. In these examples, you will see how to calculate for plastic, for compact, for semi-compact, and for slender, following their necessary conditions. So for you to determine whether it's class 1, class 2, or class 3, or class 4, we also have a table. This is the table 11 on BS 5950, of which you can see plastic, compact, and semi-compact. You can see the strain there. The strain can be gotten by taking the square root of 275 divided by your strength that you got from this particular place. This is your design strength, PY. If it's 275, you bring back the 275 into the formula at this point. As you can see, follow the cursor, you can see the PY, that is your design strength. The root of 275 all over 275 is 1. So you can now go back to your table, which is this. From here, you can see the value of your small d, of your small t, of your capital T. These are the main thing you need for determining the section classification. To get your plastic B over T, the B is gotten from the table I showed you earlier above. Is table 2. This particular table, you can see your B over T, but in this case, they requested for D over T. So our D is gotten from what? That's the depth between the fillets, and our capital T is what? The thickness of the flange. So you bring all these two together. Once your answer is less than this particular value, you can say it's plastic. Between this three, you can pick your specific value, then you calculate and say the section is class 1, class 2, or class 3. So limiting width to thickness ratio, elements which exceed this limit are to be taken as class 4 slender section. After considering the whole of this table here and the answer you got is higher than the values here, automatically we can conclude that it is a class 4 slender section. So the next thing is our shear. You have to determine your shear. You can see the simple formula for determination of shear. You can see your FV, which is your shear load, your shear force we got from the shear force diagram earlier. And the PV, our PV is given here, is needed also for many things. Our PV is the shear capacity, and the formula is given as 0.6 multiplied by the design strength by AV. Your AV is the shear area, and is given by small t multiplied by d. Of the small t and the big D can be gotten from this table. You can see the small t is your web thickness, and the big D is the depth of the section. So you can calculate, but there are conditions necessary for design of shear to know whether you are going to use low shear and moment capacity or high shear moment capacity. For you to have a low shear moment capacity, then the low shear load must be higher than the high shear load. That is, your 0.6 PV should be less than your shear load, and it should be less than what? Your PV, which is the shear capacity. Same thing applicable to high shear moment capacity. Your shear load, if the load gotten from the shear force diagram is greater than the product of 0.6 and PV, you can calculate for high shear and moment capacity. In some cases, it can result to buckling. You have to test for buckling and many other things. It has specific formula. In the next example that I'm going to do after this introduction, you will understand how to calculate for low shear and moment capacity, and how to calculate for high shear moment and moment capacity. So the next thing is deflection. For your deflection, this is one of the necessary table, and all other things needed under deflection are simple basic formula that you can add. Like you can see, for uniformly distributed load on this simply supported beam, you can use the formula that you are seeing here. The same thing applicable to the point load on this simply supported beam. We have for cantilever with uniformly distributed load, we have cantilever with ordinary point load. So deflection for standard cases, the E stand for elastic modulus of steel, and for steel as well is 205 kilonewton per millimeter square, and I, which is our what? Second moment of area of the section. It can be gotten from this table also. You can see the second moment of area axis for x-axis and for y-axis. This is it. You can pick the suitable one of your choice for the value you got from your calculation. We have for web bearing. According to clause 4.53.1 of BS 5950, provided the distance from the concentrated load or reaction to the nearer end of the member is at least 0.7 multiplied by d, and if the flange through which the load or reaction is applied is effectively restrained against both rotation relative to web, lateral movement relative to other flange, you can apply this formula and get your answer. In the next example of the next tutorial, we'll apply all this formula, calculating from beginning to the end, applying all the necessary design steps for beam. And last, the number 7 is contact strength and support. It's very easy. We apply the formula. You can see your B1 is given, R and T, everything is gotten from the table. PY, as we say, which is our design strength also. Then you apply, you get your contrast strength to get value for PCX. So for web buckling, you apply this formula, and there are conditions to apply. When you have this condition that is less than 0.7 D, the buckling resistance is calculated using this formula. If the flange is not restrained against rotation, you can use the second formula. Subsequently, you will see the application of this formula. Just take note of them. As you can see, following the mouse, you can see LE. LE stands for what? L subscript E stands for effective length. It's very, very easy to get your effective length based on your condition. It's gotten from this table, table 13 of BS 5950. Pick it and calculate. If you have both lengths fully restrained against position of plan and it is normal, loading that is due to the loading condition, I can pick 0.6 multiplied by the length of the beam. Same thing applicable to all different conditions of the beam. So the ninth step is effective length calculation. So it's the same thing as the part of applying to this formula, the effective length of this formula, the same thing. So we are going to do effective length. You pick from the table, you get your value. Then finally, we have the buckling resistance using the conservative approach. So one thing you have to know about the conservative approach. What do I say?
The director is in that side, right?
So the buckling resistance using the conservative approach of clause 4.37 sometimes might involve trial and error method, as the buckling resistance moment is much less than the actual imposed moment. In some cases, you have to design the beam so that the beam will not fail with lateral torsional buckling using trial and error method. In some cases, you can pick more suitable sections. So subsequently, in the next example, which is going to involve high level of calculation, applying the whole necessary step, you will understand the whole process and the application of this 10 step. Please endeavor to subscribe.